Hi, my name is Isaac, and I'm lecturing about the VA patch bypassing. The VA patch is a kernel security patch, and it's preventing a very core of exploiting in Linux at the moment. People are making research on exploiting. They usually take an application or software, testing on different platforms and using targets as return address. The VA patch goes against this, just saying each process will start with a randomized stack pointer, and it's making impossible to use absolute return address. So there's a new approach to bypassing it. I'm going to show 5 methods, which separating into 2 groups, a runtime groups, which is the stack juggling methods, and an offline solution, which come along. We will start with wet-to-wet. Basically, it's based on 3 principles. We got the write instruction, a previous located pointer on the stack, and of course, the null byte overwrite process. As you can see, we're going through the stack, and we have an already pointer there from our previous stack frame. Once we got this, the pointer doesn't actually have to point back into a buffer. It will go to a process that's called byte overwrite, a single 1-byte alignment process. The gap between where the shellcode, where the buffer is located, till we get to this pointer, we will have padded with wet instructions. Each wet is using like an op. We will just slide through the stack like this. And the last wet will jump directly into the pointer, and the pointer will jump right back into the buffer. So here we have the vulnerability. It's a very classical buffer overflow. We will start by disassembling the program. So after we disassemble it, we can just put a breakpoint before str copy, so we can have the idea of which is the buffer variable address space on that stack. Once we figured and calculated the buffer variable address space on the stack, we can start examining and appreciating which potential return address can be used to the exploitation. As you can see, we got one, but it's not a current one which points exactly, but it will do good after we have the null override process. What exactly is the null override process? It's a result of a few factors, the little indianity and the trailing null, which is a result of how C language handles strings. As you can see, the lower byte is being replaced, nullified, which makes the pointer valid and useful for our attack. So this is the actual exploit. It's a little bit truncated. As you can see, instead of giving away the return address, we simply use the red slide. And the shellcode is a very primitive, simple one, just to show that it works. So the next approach is red to pop, which is quite similar to red to red, only meant to attack inside a function. If the function accepts the pointer to a buffer, which is in this case a buffer that we can control, we have a perfect return address. Ironically, the same process, the same null byte effect happens here as well, but we want to preserve the pointer, so we need a new combo. We can't use the first argument because it does suffer the impact of the null byte overwrite, but if the buffer is passed as the second or higher argument, we can actually do refactorize it. We just need a new combo. So what is the new combo? It's pop followed by ret. What happens is the pop will swallow the first argument, and the ret will jump directly to the second one. Let's look about on our vulnerability program. As you can see, we have the buffer passed as the second parameter, the function, and we got the init passed as the first one. So where can we find pop followed by ret? Normally, a program that isn't been compiled with any optimization will generate, GCC will generate a leave instruction to restore the previous stack. To avoid this dependency, we'll refer to the CRT. Reporting the CRT to this mission is kind of useful because the CRT doesn't have influence about whatever the program status has been compiled with or whatever optimization flag it has. And the CRT itself is also a very rich source for finding all sorts of assembly snippets when the actual program doesn't provide one. As you can see, we have the frame dummy function, and it does manually restoring the stack, not using the leave instruction. So having this address, we just ship it away in the actual exploit as the return address. The third method is write to AEX, which is kind of off the stack at the moment. What happens is in the convention, when a function has return value, the compiler is using AEX to store the return value itself. So what we have the function returning with our buffer in it. All we gotta do is gonna find a call or a jump back to this register, and we got everything sorted out. So this is our program, this is our vulnerability. As you can see, the program actually returning back with a string. Now, let's see where we can find. Again, in the CRT, we can find part of the global construction initialization. We can see call to AEX registered. Using this, we can have a provider return address back to the buffer. Okay, so this is the exploit. As you can see, we passed away the return address as the line itself to the CRT. Right. Now, to the last method in this group is return to ESP, which is kind of popular among Windows exploits, not quite popular among Linux ones. What happens is we have all sorts of data, and data can have double meaning, depends who is looking at and format offset. We can have hardcode value, which is to the program looks perfectly normal, but looking from the CPU perspective, it can be translated into an instruction. As you can see, this is a normal program, which happens to have a very special value in it. This value is actually translated back to jump to ESP registered, which is a crucial register in the exploitation. Now, this is how it's actually been implemented. As you can see, the E4FF in the little indianity is jump to ESP registered. So what happens is we tearing down the instruction into bytes, and we perform an offset jump into this code. As you can see, what began as the one line end up as having jump to ESP. This is, in the turn, will be used as return address in our exploit. All right, the last method is a bit kind of offline. It's originally designed to attack an already running process, which means we have a daemon, OpenSSH, inetd, and all sorts of stuff. What happens is before the exploit actually goes to work, it does homework, which means access the process proc entry, and from that proc entry, it fetch up the initial process ESP. So let's do a dray test. What we can see, we just take init process, and we pull out its initial ESP, converting to X, and this is the process stack start address. So having the vulnerability is a very simple daemon, Dumbo, which happens to have a overflow in the lower section. It reads more bytes than expected. What happens is we start the daemon, get the initial ESP value, attaching to it, putting a breakpoint before the actual read occurs to get a sense of what's the current buffer variable on the stack, shooting it down using a simple buffer overflow line, going back to the debugger to check what's the buff address variable was. Now, having all the data, we can generate a ratio, a figure, between what's the initial ESP was and what's the ESP at the time of the attack occurred, assuming if we will repeat the same flow, the distance, the ratio, will always be the same. So we can disregard what's the exactly ESP current value. So what exactly does it involve? We have a function that retrieves the process initial ESP by accessing its proc entry. We're having the exploit itself, which, as you can see, using the magic number we provided from the research. And basically, every time when we attack, we can disregard an absolute return address and just generate one before we actually attack. This way, the exploit has made homework before attacking the actual daemon. So how are you guys doing? Thank you very much.